Hi everyone, thanks Russell for the introduction, and this has been a project that we did earlier in the year. It touches on a few topics that have been covered today through the electrical design, safety, risk assessments and operational considerations. Something I had to relive, recreating this PowerPoint to kind of go through the project again. Something I didn't really want to relive, but it's a good share for this audience, and I learned a lot through the project. So there's a few photos, and I'll probably try not to go too fast over the information, but at the end of it, like, again, reach out to me. I'll try and explain all the details that aren't covered. I'm at Ulan West. If people don't know me, I've been the EM out there for 4 years. This is the first real shutdown that I've ever been exposed to, and I guess the duration of 4 days had some complexities that we had to work through. And the time periods, you don't really get much notice between locking it in and then actually going on the project path. So, overview from the agenda today, I've got a bit of a site overview, where we are out at Ulan West. The electrical overview, as we stand, is quite normal. Background for the power outage, alternative power options considered, our expected position for the underground operation during the outage. That was probably critical for us. Locking the dates in, it becomes pretty surreal when you get that notice and it says, these are the dates, you will be off for 4 days. And the actual position and that critical infrastructure we had to power for that entire duration. So a couple of nice pictures through the slider that we've picked the best ones we could share to this audience. And this is the box cut down at Ulan West. So it was a open cut that we've gone into the high wall there, and we're basically in seam, no drift, all relatively level, which plays in a few of the issues that we have on site. Ulan West operation, another overview of the box cut there from an aerial. 4 hours northwest of Sydney. We're out near Pleasant Old Mudgee. We've got access to Port Newcastle via rail. We go through surface ops, and they clean the product for us. There's 2 adjacent mines, Ulan Underground, if anyone's familiar with the area. We both feed onto a common rail loop, and we export our product. High capacity longwall system, we production record last year was 8.7 million. So I guess we're typically a 5-day-a-week operation governed by a rail loop, but we do have the ability to turn a lot of the equipment up, and that's kind of 7-day-a-week production numbers speaking for themselves. Normal reticulation for the site, so we're very well laid out site. We've got, I guess the longwall intention was always there from the beginning. We've got borehole pumps, which are powered from our adjacent mine on their feeder, their 66 feeder, which steps down to 11 and 1,000 volts from there on. On our feeder, the main 66 for Ulan West, we've got 2 transportable subs. That's the main infrastructure. That's all we've got, 2. And overall capacity with the mine in normal operations, 14 MVA. So not huge in comparison to different operations out there, but relatively large. And that redundancy between those 2 transformers is there as well. You look at it, we've probably got a good redundancy there. 2 that could rely on 1. Main vent fans, again redundancy, it probably flows through this whole presentation. We've got 3 1.7 megawatt motors on these vent fans, and we've got 3 of them, 3 individual switch rooms, and they all can all do the job. We're currently running 1 that does the whole mine ventilation. Longwall, those production records set the other year were 2-year longwall block, so no longwall step rounds or anything like that. We've got 8-kilometre longwall blocks out the back there, 400 metre face, 11 kV AFC. The install power on the face is 7.5 meg, and the conveyor is 6.2 meg. So that's all at full install, and as the conveyor retreats, it's obviously we drop stuff out of the system. Dewatering, back end of these blocks are quite level. Further in by as we kind of start down dip, and we've got an area where it's quite level. There's not much elevation or change in elevation where we end up with water pooling is one of our concerns out there. Not much gas, but a lot of water. So we've got those borehole pumps that are now averaging 8 megalitres a day. We step up about a meg every block we go across with a bit more catchment out of the GOF, and so along the capacity we see a bit more, and 15 megalitre peak. So we see that when the longwall first takes off and we have the first roof fall in the GOF behind us. So staging the water underground to those borehole pumps with electric submersibles and air pumps. So background for the outage. We've been pretty fortunate out there. We've never had really any issues with this switchyard 66, pretty straightforward. You'll notice that Ulan 1 feeder, which is powering the original underground, Ulan Underground, which is adjacent to Ulan West, has a bypass provision. Ulan 2 feeder adjacent to it, there's no bypass provision. So when we've been told that they want to replace our circuit breaker, which is an old oil-filled breaker, we were in for a full outage to replace that. There's obviously considerations of what we're going to do next. The 4-day outage was considered a big risk to our water and our strata. So the longwall being stationary, being in a position where we were, all the rest of the effects for turning an underground coal mine off for 4 days, what would they look like? So we did the high level, also bird's eye view, or just checked out what it looks like at that position. And spoiler alert, the breaker was replaced and we did get back on in 4 days. So I'll probably share the new breaker, which we had a previous outage with the oil-filled breaker getting to that point where it was leaking. Maintenance was becoming a concern. The supply authorities informing us that we're going to have potentially more outages and we're running a risk. And we all could accept oil leaking out of a breaker. It is a big risk, and if it happens in the middle of the night, it could be way more than 4 days. So a planned approach was accepted as, yeah, that's the logical and the right choice here. We have to support this. We looked at alternatives to power the mine. So we're not all jumping up about making it hard. So we looked at bypass provisions. So in the switchyard, Ulan 1 feeder has a bypass provision, and that hasn't been used in the time I've been there, 6 years, and it's been there for a while. But there's concerns with changing to a bypass feeder. You've got to look at other aspects, and we considered putting a bypass in as well, but outages to do that and not seeing an outage for the last decade wouldn't really warrant that work to pursue it prior to this situation we found ourselves in. But we did consider having an external bypass provision between our 2 feeders because they're powering 2 Glencore mines, Ulan Underground and Ulan West. We had that ability to consider that. To install that external bypass provision, because it wasn't going to be feasible inside the yard, there wasn't enough room. We considered it outside the yard, but again, it didn't really have an appetite because the outages were going to far outweigh the benefit they would see for it for frequency that we do these tasks. So we stepped into the generator realm, something that has hairs on it, reliability, types of equipment, amount of generators, and the whole process. So we had the luxury that Ulan 1 feeder was staying on, and our borehole pumps, one of the critical assets for us, was remaining powered on a solid supply, and then Ulan West would power the rest off generators. So we kind of made that decision pretty early in the piece and said, like, we've kind of considered the others. We've put them across the people involved, SLT, and we all kind of found ourselves in a common ground that's making sense for both operations. Expected position for the mine. So the water issue I was talking about there, shown on the board, that's our companion road at the back of 7 block. So it doesn't take much for the water level to come up quite rapidly, and the water level is as mined. So we get a bit of an idea after we've mined these areas, what the RL is, what the fall level is, and we map all those parts of it so we can learn moving forward, and all the water areas that have pooled across the mine in the previous activities, you can kind of see them scattered across the mine plan. So our expected position for the outage, we had an idea that mid-May we're going to finish longwall relocation. So yeah, we'll be back on coal and the longwall will be retreating. We're going to be transitioning out of an inrush control zone. So that's where we're going through a low level. There's a body of water next to us. And if the longwall stops or if we lose pumps, that's our critical time. That's going to flood the equipment and that's going to have us down for a period. That water make had increased from 7 meg to 8 meg from the previous block to the new block, and we've just seen a 14 megalitre peak just after the walls come in. So we've dealt with that bit of water that's come in and got it all back down to our normal averages, and we're managing it. But we had an idea of when we had to have this outage. We couldn't have it any earlier than July, and we couldn't have it any later than September. That's where we had another inrush control zone that would be transitioning through, which would be same position again. So you leave it too long and we'll be back in the same boat. So we got to a point and we said, look, this is where it's got to be in our best position for this operation. And we suggested this date in July. Well, the start of the July was the date as soon as you say July. Start of July is where it fell. It affected multiple companies, stakeholders, and every negotiation we tried to make with the supply authority wasn't just affecting us, but it was affecting another 3 operations down the road. And by changing it on our side, it was going to affect them as well. So we didn't get to any really, I'll look at a few of the people in the room that it also affected, but we didn't get to a point where we had a stalemate that we're all pretty aware of how it affects other operations, and there was large shutdowns planned. We all kind of knew that once it's locked in, we're locked in. We've got to work towards it. And we're having fortnightly catch-ups with the regulator to make sure we're kept on track, because there's a lot of works happening in this switch yard for upgrades, major repairs, replacing components, which were all in a sequential order to get to the final circuit breaker replacement, which was going to affect our operation. So we got to that point where we found ourselves where we expected to be. So we'd finished wall move. We finished at mid-May as we expected. Mid-June, the longwall retreated 400 metres, and we're approaching 80, 79 cut through in the tailgate, we'll call it there. And we're basically in line with where we want to be. So the inrush control zone's the green highlighted section on the block we've mined. That's the 400 metres we've retreated, basically to go out by of where the water was expected in that area. We have a as mined map or a 3D model showing that where the longwall did start, we've got the lower areas, which are blue, and we've got the high area, which is the gradient of the red. So we started our longwall in an obvious risk zone. All the floor profile and all the mapping after we've mined the area aligns with what was mapped out with survey and the rest of our mine model. And we've started progressing out of that water inrush control zone. So over the 400 metres, we retreated. We started at 292 RL and we got ourselves up to 295. So 3 metres elevation doesn't seem like much, but it's really just that catchment enough to take that inrush of water and somewhere to give us a bit of time. So we got to the point where we had to look at what was critical for the operation during the outage. Underground coal mines, so we've got all the communications and power articulation for normal amenities and the rest, so they were kind of a given for everything that operates normal. We're going to power all amenities, our monitoring, our communication systems, and avoid changing our redundancy. So they've all got UPSs, generators, which are built into the system. They're all fixed electrical installations. The power supply we're going to implement was going to be above them in case that fell over. They would have the redundancy that we expect for the normal operation. Main vent fans. So we've got those 3 main vent fans we're talking about, which provide access for underground, but also they interlock our underground power. So having them operational meant that the rest of the mine could be operational in a normal aspect, and the plan was to provide full capacity and allow the operation to continue as normal or consistent as they could. So ventilation quantity and power interlocking remained the same. The moral with the whole design or the focus around this critical infrastructure was keep it as simple and as close to normal as possible. The least changes will avoid changes back. Another aspect we had was that longwall we just spoke about. Hydraulics on the longwall, obviously keeping the roof up. And if you have that off for 4 days and a couple of legs are bypassing, or there's a leak in those hydraulic or emulsion circuits, we're going to have concerns with roof integrity and weighting on the wall, which you could get to a point where we were in a different situation, not a water risk, but an actual longwall that we're going to have an asset that we're exposing to bigger risks. So that being stationary allowed us to run it at half capacity. So we had the emulsion pumps mapped to consider what was appropriate, and basically the 4 normal pumps were overkill. One would have done the job, but we allowed for 2 just to give ourselves that margin. And our dewatering system, obviously, so that had to operate at full capacity. Without that full capacity, we do run in and out of full capacity with that system all the time. So that was set up with the air pumps, the normal electric pumps, and changing the compressed air now had to be across to diesel compressors. We weren't going to power that via generators and power a switchboard and other concerns electrically. We're just going to power them straight off diesel compressors. So then we got into the detailed electrical design. So electrically, I think everyone's had a bit of a play with generators here and there. It's not the easiest when you start combining multiple generators, running for multiple days and having that concern about reliability, redundancy and other aspects we've got to consider. So we broke up the sections to say that we're going to look at the electrical design for the whole system, specifically around the generators, network reconfigurations, the generator earthing design and installation, which we followed and tested, network fault levels with the generators, the comparison with new versus generator fault levels, electrical protection review, main substation, SLD through to the installation, and the vent fans SLD through the installation. And that's one of our main substations, 15 MVA, 15/18, but we don't ever use that 18. So the common philosophy for the whole outage was understand our base loads, have it capable of black start. If we lost the generators, we'd see ourselves in that situation. It's 4 days. We have to be able to start this operation during those 4 days to make sure that if we lost the system, we could restart. The grid's not coming back on. They're replacing a circuit breaker. And earthing to match the system. So we want to keep everything as close to normal as possible. It meant less changes and less changes back. So the vent fans on a normal maintenance day, we're sitting at 3.5 MVA. That's kind of where we'd find ourselves in the outage. We're not going to be doing any production or any additional tasks in a period which we wouldn't have capacity to run the rest of the system, the rest of the belts. So we're running a full capacity of one of those fans. That was our normal ventilation. The transformer which run those fans is only 2.7 MVA. The largest motors are 1.7 meg, powered by triple VF. And we came with a generator supply capacity of 5 MVA with a redundancy N+1. I'll go into that with a bit more detail later, but the oversized capacity there was for a vent fan changeover, so we could run 2 in parallel. If we'd had a fault, the second fan could start. So there's actually enough to not interrupt our ventilation by having enough to start the second fan simultaneously to the first. Main substation, so we're reticulating power underground, surface and around the mine. So we had a complicated network with that, in essence, that we've got a surface and underground infrastructure that has interlocking and additional requirements for that, which we didn't really want to change that much. You're changing a system that's proof tested. It's got a level of reliability and redundancy, and every change you make, you've got to undo at the back end. So specifying that system, we ended up with the largest transformer was 5 MVA. It's at the end of the run, so in rush for the longwall transformer that sat at the end of it. largest motor was 250 kilowatts, so starting a DIL motor on a generator, had to make sure we had that capacity to allow for that. Wasn't going to be a concern at 250 kilowatt, and capacity for the generator system got chosen at 4 MVA. That was, again, N+1, so we had redundancy in these generators. They weren't the real concern at the end of the day. Having an extra generator, it was all the other parts that go along with it. So we rejigged our network to power from the generators. So surface and underground reticulations were kept as close to normal as possible. Longwall feeder, which is on its own dedicated feeder off one of those substations, typically was reverted back to the development feeder. It had just been installed during wall move, and it was logical to swing that back across without any longwall loads off it. So it was back to an installation reticulation, how we had operated slot previously. Earthing separation between the underground and surface was going to remain. We weren't going to install these generators in a position where we didn't have screens on our 11 kV cables continuous, and bridging gaps that we obviously have a system designed to avoid that, and fault limitations. We wanted to make sure that we had a fault restricted network in this situation as we do in our normal operation. So we got into the earthing as early as we could, the design and the installation. We've just locked in the dates 3 months prior to this outage, and we've got a lot of groundwork to cover. So we had to look at all the possible scenarios of generators before anything had been locked in, and we had to start building earth grids. So the earth grids are probably looking like they're overkill, but we hadn't confirmed orientations, generators numbers, equipment numbers, and the rest of the layout. So we end up designing it as existing. So we're going to match the existing earth grids, look for the similar performance out of those, so that we could end up with the same risk profile and go from there. Low voltage on the generators was 5 amp fault limitation, just standard for an underground coal mine. High voltage, 10 amp fault limitation on the 11 kV. It was a common bus with these installations, like standalone installations to each other, but that matched existing, and the grids were large enough for different generator installations, so they'll map to our areas. We basically picked a profile for the grid which would allow for different configurations, and we didn't know if we'd put 2 installations in the one site and backfeed the other at this point in time. And all equipment was installed with protective earths and equipotential bonds as per the technical references for standalone generators. So I guess we looked at a lot of this information that everyone's aware of, and we've talked through the day that it exists on. It's there for everyone to learn from and use, and that guidance was used through this process. I will reiterate, we did use an earthing engineer. There's a few aspects you don't want to get wrong with your earthing, especially when you're changing it, extending it, and having all those items looked over thoroughly. It ended in a good result. The testing of the installation. So we've had our 10 amp fault limitation. We tested the grids, and we've got 2 ohms, and we ended up with an EPR of 20 volts at our vent fans. We're pretty happy. We tested continuity back to the grids, and they were connected at 10 milliamps. So we had a successful day there at the vent fans. The main sub, same situation, again isolated from the other installation, hazards from the 11 kV network, half an ohm grid by the time we extended, and there's a bit more earth in the ground out there, 5 volt EPR. So again, we're pretty pleased with those voltages for what it meant with step and touch potentials. And we measured the continuity back to the grid, so we had that connected, and it checked out. Involving that earthing engineer, one of the aspects that was obviously a concern was the 66 kV network, which supplies a mine, has no earth fault limitations. So we had an EPR estimated of about 720 volts if we had an earth fault on the 66. To validate the grid around the 66 kV, we completed current injection testing to assess all those step and touch potentials across the generators, across the existing grid, to make sure that the new and the old installations are all within an area that we're comfortable with. And the generator equipment wasn't turned on with the 66, so we didn't want to extend our risk profile to have extra equipment that people worked on in that area while the 66 was energised, so that the installations weren't at the main sub weren't kicked until the morning of. So we didn't do much with those generators. The vent fans weren't as exposed to that risk because we were further away, and there was segregation from the 66. We're talking close to a kilometre away from that, so it's really the main substation where that became a concern with the fault limitation not being there. We ended up with new network fault levels, as you can expect. Generators have a different profile to the coal-powered fire station, coal-fired power station up the road, which is giving us a pretty reliable supply and pretty good fault levels. We mapped it across our whole network. We involved a couple of different people to help us get all this information and to determine what it would look like running the site off generators. We had 2 installations, a 4 MVA and a 5 MVA. So looking closer at the 5 MVA at the top, we had 7K, and it would have been nearly double that at some of the points. We considered what it looked like with different generators, considered a TARP with the fault level decreasing with every generator that would turn off. So if we found ourselves in a position where one generator fell over, we'd have to actually consider if it was appropriate to turn the entire installation off until we had them all running again, because we ended up losing that fault level to a point that wasn't appropriate with our settings. And then we had a fairly substantial fault level on the low tension 415 bus of these generators that we can appreciate. So look, we had remote switching that came with the lift gear that we hired to control those aspects, but we had two sides of the fault levels, so quite small fault levels and quite high fault levels on the 415. So we compared that to our normal. So 4 MVA, that was our main substation installation, and that supplies the box cut. Our box cut switchboard, SB105, basically had a look at what it looked like in our normal model and compared it to our generator scenario, where we're looking at half the fault level. So it's an obvious concern that just appeared that that's something we're going to have to address and make sure that we've got appropriate settings to consider what it looks like with half the normal fault level. So we jumped into our protection review. We had to look at everything we were going to power, ensure that they'll set appropriately, and we used some guidance from some more information off the broader industry, but we found ourselves in a position where it was more appropriate to lower some of our upstream settings rather than going to every last supply and adjusting settings. So we accepted the loss of grading rather than change the entire site and having grading ideal for a 4-day outage where we're only powering a very small percentage of the operation. We used EESS 005, the technical reference for electrical protection and earthing, just around ratios which are acceptable between your short circuit trip level and your actual fault levels. Again, guidance. We kind of use this philosophy for a lot of our protection settings across site, and we don't want it to be more than 50%. That's our target. We then considered the final aspects of right to the last motor we're going to power and consider if there's equipment we shouldn't be powering, and we found ourselves initially considering not powering the development equipment would be appropriate, and our decision was supported by this review. We kind of found ourselves on the mains minor down in a pretty easy, not a high risk area, that it's still probably not appropriate to power it with the ratios going well above what our normal is. So there was a decision was supported to leave that equipment isolated, and it's moving equipment. It's the most likely equipment that we're going to damage a cable in and actually have a short circuit or a arcing event underground. So that concern was supported, and we kept that equipment isolated. We came up with our final designs. We came up with a power design of how we were going to lay this all out. We looked at the types of equipment available and trying to keep that network as close to normal as possible. So we didn't want to make any changes underground, and the physical locations were chosen with surplus room. That was back to the earth grid. We had a lot of equipment arriving that we had to make sure there's enough real estate to actually fit it. So even after you've given the consideration to, I want room plus more, it still ends up being pretty tight. This is our main sub installation, where we've got the 4 generators either side of the step-up transformer, where we've got our 415 to 11. And around the back, it's tied into a couple of our 11 kV supply feeders. Another big concern for the outage was our main vent fans. We've got Rockwell Triple F PowerFlex drives with forge control. The motors are Tico 1.7 megawatt, 750 RPM, 8 pole, 3.3 kV motors, and historically a big challenge to power these fans, not just with the size, but the drives are current source inverters, so large line side capacitance have given many of people that have had these drives headaches to try and run them off generators. So we had a concept. It wasn't new. People have done it elsewhere, and the 3.3 megawatt resistive reactive load bank was going to be our solution. Take that line capacitance out of the system, compensate for the overall leading power factor that's going to give these generators a hard time, and would reduce it once we've started. We're only targeting 0.8 power factor, so I don't know if anyone took note earlier on, but we usually run at 0.97, so we're back to a generator number for this installation. Yeah. The main vent fans, so the single line diagram here, again, very similar. All the equipment we chose was very similar to try and make it as straightforward for the people installing it, for ourselves, and it was all kind of modular. It was all going to be installed in the same kind of style. They're island installations, so they had that black start ability, and we didn't want to power any non-necessary infrastructure. So power lines that would usually supply the vent fans, they weren't powered. The generator installation was adjacent to the fans, just to avoid any extra risks for that period and trees falling on power lines. Capacity exceeded the loading, so again, we'll touch on that before, where in a fault condition we had to be able to start 2 fans or would be dropping underground power, which stops the pumps and the rest of the flow-on effect. So we had that additional capacity. We had a load bank now, which if we lose the main generators, that load bank's producing a fair bit of heat, basically a heater element, and it had its own additional generator which is powering it to maintain control and cooling. So that's just off the end. So we found ourselves with the load bank and the 5 generators, that installation, the vent fan site was at capacity for the equipment we'd chosen. With the N+1 redundancy, we still had the ability to turn a generator off, and we weren't going to have many concerns apart from those fault levels which I spoke about. Segregation of assets was achieved. So we did all the homework. We tried to find the best spots for these installations. Critical assets, we've got segregation between all the transformers, fire-rated rooms, and we've just installed 5 generators, a load blank that just says a large heater, and diesel pods all over the show. So we didn't want to compromise all those items, so space was a key part of the whole planning process. Well, that concern with the fans, that we wanted to make sure they start up as expected from generators. So we actually logged the start using the Rockwell Drive software, and the starts replicated a normal start off the grid. So that for us was a supporting factor to show that our installation, our design had worked, and we didn't have any real concerns that would die to turn off and adjust settings. So that installation started and ran. The load bank was set like I spoke about. It prevented physical capacitance removal, so we could have gone into fans, removed 11 kV capacitors, 3.3 kV capacitors, and rejigged the whole switch room to allow for not getting a load bank in, but that would have meant changes in the back end, and we didn't really want to have a large outage for the changeover. So we ended up kicking the generators away on the first, and the vent fans didn't stop after we ramped them up to speed. So it was successful. They didn't stop the entire outage, and nor did the generator. So that installation was something we were pretty happy with. There's all the operational items that supported the electrical design. So there was one thing with the electrical engineers all focusing around the specifics, and we spent a lot of time on the main vent fans to get that installation as bulletproof as we could, and to everyone's credit on site, it ended up getting there, and we were very pleased with the result. Operationally, we couldn't miss the fact that we had a massive change to the operation. We had to consider the risks with operational risk assessment. Equipment was arriving, so introducing all the new equipment to site, operational plans, refueling generators and compressors, noise with the increased noise from the generators. Like we were pretty quiet, small, isolated operation where generators were going to be a change for us, and emergency management and documentation of our learning. So with the operational risk assessment, I'll probably, like along with a lot of the other presentations early in the day, you do involve the right stakeholders. So we had 23. You find items that you overlook. We went up with 54 actions that had already been pre-populated as much as we could to make sure that the process was right with the changeover and operational plans that had already been considered that you'd have for generators, but there was additional actions and controls that we hadn't considered. Major risks were identified and controls were also identified in that process. We followed existing standards and our processes, so we had a lot of systems for all this type of equipment that comes to site on a daily basis. We reviewed all our new equipment that was arriving for the differences, and we verified control implementation. So putting those verification actions in to make sure it's at points along the installation you actually had checked that all the controls you said would be in place were in place. So it's all started arriving. We kicked off our introduction to site process. So we had over 33 pieces of equipment arriving less than 2 weeks prior to use. That was 9 diesel generators, a mixture of 1500s and 1200 kVA units, 5 diesel air compressors, 2 step-up substations, 6.3 MVA, 2 NERs, load bank, ringman unit, lighting towers, fuel trucks. So that's not the whole extensive list, but there was a lot of gear arriving. We didn't have all the resources to do this more efficiently than we usually would. People blame the engineering department for saying they're slow in introducing stuff, and this was going to really test our capacity with 33 items arriving within 2 weeks. So we followed our normal process. We had our permits, we had our operational plans completed prior, or as much as you could prior. The working your power sources, the group isolation, the high voltage permits. The priority for swapping over fans was going to be the first step on the day, because once everyone had access underground again, we could carry out with the other tasks in a controlled fashion and powering the rest of the mine. The fans allowed people to get on with their normal day. Communications were going to be out to the wider workforce to make sure that people weren't going to turn on additional loads, stuff that we hadn't considered appropriate, like continuous miners in development, and stuff was isolated to make sure we had controlled that risk of additional stuff being powered. Suitable changeovers, suitable coverage. So like I said, we didn't have additional manning that would allow for this to just happen smoothly, so we can consider that appropriate. We had enough support and the right people, I'll suggest, around the clock in case something happened with those installations. We're looking at fatigue, and all the right engineers had to have those breaks, so we brought on additional people to help with that. And restricted access. So we had all these high incident energy levels around the generators and controlling areas that weren't normal for the operation. If anyone's played with generators, refueling was probably the one that kept me up every night for those 4 days. Sites were remote from each other, so we allowed for increased fuel capacity. The generators and compressors had individual 4,000 litre tanks for that capacity. The fuel tankers had 8,000 litre tanks, and that was 7 trips a day. but we were averaging 160 litres an hour across all of those units that were continuously running. I was tracking every truck, and we didn't want to run the trucks at night time, so we'll run those 7 during the day, and keeping an eye on them, just to make sure that the show wasn't going to stop, as well as allowing enough contingency for the back end that we didn't want to have too much fuel in the pods and have to re-drain it. So there was a tight ratio of how much you leave in the pods throughout this whole process. Noise, one of the things we overlooked a bit, but got reminded with our E&C team, which it was a massive change for the operation. Our noise portfolio had changed dramatically. So noise modelling was carried out for the installations. Our neighbours aren't that close, but when you've got 4 diesel generators all humming away together, and we typically don't have anything apart from a fan running, you notice them pretty quickly if they're running or not running. And yeah, to the point where orientations of the generators and the size of the generators had to be considered. So we ended up with only 2 1500 kVA generators in the mix because the engines were slightly louder, and we opted for certain positions. So the 1250s would be on the neighbour's side to act as a bit of a shield there with that noise attenuation. Emergency management, so back to that risk assessment, we'd considered all the preventive controls. We spent a lot of time there, but we didn't want to forget the mitigating controls. If a diesel generator did catch on fire, this is a step for us, and where segregation came in, that was obviously the hierarchy, and looking at isolation of these installations to our tier 1 assets like our vent fans and our main substations. We've only got 2. The remote emergency stop, so having a provision to entirely cut off the installation instead of heading towards a generator that's on fire was forefront of everyone's mind. That's where you go to, and as you access these restricted areas, that was the first thing you saw. And then the minor spills and egress around fuel tankers, so enough egress for trucks, and if there is leaks, we had spill kits to deal with it. So the environment was always something to consider as well. We got to the point where if we did this again, we want to do it better. So both 11 kV networks required reversal. So this is the first time we tied in generators at these different points, and yep, we got them both wrong. So we allowed an extra half an hour for changeovers and had permits already prepared for that. That was something we'd considered, that this is 50% of the time it's wrong. We won't get that wrong again. But it was something that we had a slight suspicion that by phasing it out as per the generators, we're actually backwards on our site. So that was kind of like hindsight. We should have hedged our bets, the opposite. We had 16 kilometres of cable underground, and that was something that was a bit of an oversight for a general parameter, that the capacitance in the network from just the cable was about 400 kVAR, and each generator at the main sub, there was only 4 of them, had a tolerance of 100 kVAR. So any more capacitance in the underground network would have put these generators past their trip points, and as soon as we lost one, that was the rest of them were off, because that 400 would be shared across the 3 generators with 100 each. Load flows supported that we had additional capacity, but that was also weighing into the fault levels. So we had enough for more, but fault levels didn't support that as well. So our vent fans, historically through different operations within Glencore that have the exact same infrastructure, it's been a struggle in removing capacitance and trial and error, and this installation for us worked really well with that load bank setup. So but wanted to document and make sure it's available for the next people so they can continue on the journey and improve from that. Can't say much about the vent fans and general learnings. We had those long hydraulics for roof, but it did also allow the fitters full hydraulics, which allowed them to run the chain. When people can consider what they can do with what's running, they decide to run the AFC, which would be running adjacent to this, feeding into the BSL, and that's heading out on the out-by conveyor. They had fed all the coal from the longwall face onto the BSL and had piled up because the out-by belts weren't running. That opportunity was documented, and in hindsight, it was probably something we should have considered appropriate as well. That wasn't much coal across the whole face. It was only little bits and pieces, but for 400 metres, it ends up being a pile. It really did allow the fitters to do a lot of work on the AFC for those 4 days. So that was something that was appropriate, hindsight. And powering back up, it's all this equipment that you've had off for 4 days, relays, low energy storage devices, which have little capacitors in it. And we had a differential protection relay just not want to boot up on our 66. So at the back end of the day, allowing that little bit of fuel for a run over, which we did, and it was quickly running out. And then considering what the changeover looks like on the back end, we had a relay that they're pretty reliable. It just decided to pack it in. So we had a few spot fires. And then we got back to normal. So our quiet operation back in the box cut, and our vent fans were essentially back to normal, nice and quiet, and like it never happened. So yeah, this presentation is just to really share all those learnings. Thank the site guys that are all involved, as well as a few different companies that were there on the day who supported this installation, those extra resources and planning that 3 months ahead. It wasn't much time, so we had to pull on a few extra people and at least plan for it well in advance. There's a couple missing off there, but there was definitely plenty involved. Thank you.